Hello and welcome to Tommy Analytics. This is going to be a video on z-scores aimed at the introductory statistics level. This concept may appear confusing at first, but it is actually quite simple. Now this technique works with normally distributed variables. So in other words, if you have something that looks like this, some wacky distribution shape, the technique is not going to work. Now let's assume that the three distributions on the left represent the variable test scores. So these are independent and different distributions, and the red is the test scores for one semester, we'll say. Green is a different and purple is a different semester. And let's also assume that there is an observed score of 90 for each distribution, and we were going to represent that by x sub I. And what we're concerned with is the area underneath the curves. So for the red, we're concerned with how much area lies to the left. And looking at the green, on the same spot here, we'll go ahead and shade the area to the left. And as you can see, there's a lot more area. And this extends all the way out into the tail towards negative infinity. And for the purple, the same idea applies. Still at 90. And we shade in all the area under the curve, all the way out into the tail towards negative infinity again. And as you can see, there's different areas underneath the curves. So we simply need a convenient way to find the areas for any shape of a normal distribution. That is one reason why we use z-scores. It allows us to transform an observed value, in this case a test score of 90, into a standard score called a z-score. The transformation process is as follows. First, we need the parameters of the distribution. So considering we're working with the red, we need the population mean of the variable x, and we'll say that that's 70. We'll say it falls right in the center. And we need the population standard deviation of the variable x, and we'll say that that's 10. And again, these two numbers here are called the parameters, and they are very important numbers because they essentially define the shape of the distribution. And then we take the observed value x sub I, which we said was 90. We take these three values and we do the following. Take the observed value and we subtract the population mean of the variable x divided by population standard deviation of the variable x. And this is equal to 90 minus 70 divided by 10, which is simply equal to 2. And that is our z-score. We take the 2.0 and we bring it over here to what we call the standard, keyword standard, normal distribution. Now it is extremely important that you understand the terminology. On the left here, we do not use the word standard to describe the distributions because the mean and deviation can take on many different values. Whereas over here on the right, the values are standard. You will always have a mean of 0 in the center and a standard deviation of 1. The area to the left of 2.0 is the same exact area that lies under the curve in this distribution here. Now, illustrating further, let's say that we look at the purple distribution and we'll say that we have same mean and we have a larger standard deviation. And we'll go ahead and take the same observed value of 90. And what we want to do here is calculate the z-score for the purple. And again, these two numbers here are the parameters. And going ahead with the calculation, we get 90 minus 70 divided by 15, which gives us 1.33 repeating. Taking that z-score over here, it's going to fall approximately right there, and all of the area to the left of that 1.33 repeating, I'm just approximating here, that is the same amount of area that lies to the left of the observed value of 90 over here in this distribution. So we've seen how the z-score gives us a convenient way to find areas under infinitely many curves, because if we look over here at these distributions, there's infinitely many shapes that we can have. Now another use for the z-score is as a measure of relative standing. So in other words, this 90 here, this observed value of 90, lies 2 standard deviations from its mean. And if we do the math on that, we go ahead and take 70 and we add 2 standard deviations, which is equal to 90. And just going further, it's 70 plus 2 times 10 equal to 90, because the standard deviation is 10 here. And the larger the z-score is, the further out the observed score lies in the distribution. If we look at the z calculation in the numerator, this effectively gives us the distance between 70 and 90, and when we divide by the standard deviation, it puts that distance in terms of standard deviations. So the z-scores that we get are actually the number of standard deviations. The 90 lies 2 standard deviations out from 70, and if we take that 2.0 and bring it over here, we get 2 standard deviations out from 0. Now I just want to make a note on notation. You might see the z-score calculation represented like this. Now the problem with this notation is that it's not clearly referencing the variable that you're dealing with. In other words, here we're referencing the variable x, so we need to put that variable as a subscript so it is clear as to what variable we are referencing. We could perhaps be referencing the variable x bar. We could maybe reference that, and in which case we would have to use the x bar subscript. So when you further study statistics, it's very important to keep this in mind so you do not confuse yourself or anybody else. Now just to recap, we use z-scores as a convenient way to find areas under curves, and we also use it as a measure of relative standing to see where an observed score lies in a distribution. The z calculation is also referred to as standardizing a variable, and we usually use z-tables to find areas, again for convenience, so we don't have to resort to cumbersome mathematics such as calculus. If you have any further questions or comments, please post below, and thank you for watching.